Okay. First, thanks a lot for the invitation to this wonderful conference. Today, I'm very happy to talk about our recent work on some high loop this high multiplicity 2-loop 6-point and 3-loop 5-point Feynman integrals. So this talk is also about a Feynman integral, but it's somehow more on this computational side. Okay, so it could be a complementary to the previous talk this morning. Okay, so first I list my collaborators. So our work on this 2-loop 6 computations are from these two papers. That's a collaboration with Professor Johannes group, the postdoc Julian, and also the postdoc Julian, also the student Antonella, and also Ticcialo from Bologna, and also this PhD students from Humboldt University. And then we are also working on this kind of 3-loop and 5-point Feynman integrals. So that's some paper, okay, work in progress. And also some of the computation is from our recent package. So this package is called NEAT IBP. I think David introduced that a little bit on Wednesday. So this one is an algebraic package to help you to do this kind of IBP reduction for Feynman integrals. Okay, so this is the outline of my talk. So first, I will still say something like why Feynman integrals, why we want to do some kind of analytic computation. So the main topic for today would be the recent published paper about 2-loop 6-point Feynman integrals. I will also say a little bit on this 3-loop 5-point Feynman integrals work in progress. And also I have a side plot. So since I come here, I decided to add 4 slides on some kind of a slightly off-topic story about a 2-loop space-like splitting amplitude, just to show that this kind of analytic computation of Feynman integrals is very useful. Okay, so that's something, okay, quite trivial for many people, but I still want to say that maybe many of you already have more advanced technologies than Feynman integrals. I would emphasize that for today's quantum field theory, this Feynman integral computation is still quite important. It's definitely still important for precision physics, for the LHC or for the future collider. And it's also very important for some formal problems like this NX4 supergravity UV finiteness problem. We have expert JJ here. So we also have this kind of very important computation of Feynman integrals. The purpose of this kind of computation is to try to calculate the gravitational wave template. So today is still something quite useful, still a central topic in quantum field theory. Okay, so why do we want to do some kind of analytic computation of Feynman integrals? Okay, so of course, so this is a mathematical aspect of scattering amplitude conference and workshop. So we should definitely focus on this kind of analytic aspect. But I have to say something in general first. Okay, so nowadays we have some powerful software either based on this so-called EM flow method based on numerical differential equation or some kind of SecDec, PySecDec or Fiesta, this kind of numerical Monte Carlo method to numerically calculate the Feynman integrals. They are developing very fast, but I would say still that's point by point. So each time you spend some kind of computing resources on one Feynman integral family and on one fixed point, you get one number. But if you want to get this kind of functional dependence, you still need to do some analytical computation. And also I will show that for some of the 2-loop 6-point and 3-loop 5-point computation, this kind of numerical work is not enough. You will find that it's beyond today's computing power. So the second thing would be the theoretical aspects, okay, for Feynman integral application, okay. So sometimes you want to check some properties in quantum field theory of the perturbative QCD, okay. You cannot just rely on this kind of numerical Feynman integral computation. So this is a side plot I'm going to show today. So there's some work, it's a little bit off topic, but it's quite interesting. So I show this today. That is about the computation of the 2-loop NX4 superYAML theory, space-like collinear amplitude. So this one is about an older question. So do we have collinear factorization or do we have strict collinear factorization, or do you have some kind of factorization violation for the amplitude level? Okay, so this kind of yes or no question, okay, cannot be, well, justified by some numerical work, I would say. So we did some analytical computation of the Feynman integrals. And I also say that, okay, maybe we have heard more talks about the gravitational wave. So in this kind of gravitational wave computation, you use this kind of QFT method, but in many cases, you really need to do some kind of analytical configuration. So in that case, the pure numerical work is not enough. So I try to justify today this analytical computation of Feynman integrals is still very important. Okay, so I think you already see this kind of similar slides maybe several times this week, but here I just list our main method for this analytic Feynman integral computation. Of course, there are many, many different ways to do it analytically, but mainly we use the canonical differential equation to do this. So here I call it the modern status. So of course, okay, so we already heard that this kind of differential equation, the Feynman integral family is called I. We take some kind of a derivative, and if the right-hand side is proportional to epsilon, we call it a canonical differential equation. So nowadays we have a lot of developments on this direction to deal with more complicated Feynman integrals. So I will emphasize something like this. So to establish this kind of differential equation, you definitely need IBP relation. So here I just list some recent work, okay, some packages from China, so including our work. So first, there's a package called Blade from Peking University by the author from AM Flow. So they try to make ansatz of a simple IBP relations, and then they use a finite field method to really fit this kind of simple relation. And also for our group, we have some package called neat IBP. That's a algebraic geometry way. Try to construct some kind of syzygy solutions to construct simple IBPs. Oh, well, that's for different people, different. So for example, in their language, the blade, the simple means you try to construct something only with input integral and mass integral. That's called simple. But not in this row-reduced form. It could be 100 input integrals summed over equals a sum of 8 mass integrals. That's called simple. They have to get the mass integral first. Yes. Yes. Yeah. But numerically by finite field to get this kind of state. Okay, another kind of development which is important nowadays is from my collaborator, okay, in Hans group. So there would be a new package called Effortless next month, okay, on archive about how to find the very complicated odd letters in a differential equation. We use this kind of thing to determine the alphabet is, well, especially if you have multiple scales, that's quite difficult, but this one can, well, do it in, well, effortless way, okay. So first, I will say something like off topic, this kind of side plot. So I say this, one thing is I try to show that this analytic computation of Feynman integral is still very important nowadays. Another thing is since I'm in Florence, so I show this slides in memorial of Professor Stefano Catani, who was working here and who unfortunately just passed away this year. Okay. So we did some computation from Feynman integrals. So there's something called a two-loop NX4, okay, space-like splitting amplitude. So I will explain what is splitting amplitude. But here I just say that about 12 years ago, Catani proposed a paper called space-like versus time-like. So his idea is this kind of strict collinear factorization only happens on the space-like the time-like configuration. For space-like, the strict factorization is breaking. Okay, and he did some prediction on this one loop, two loop. But for two loop, space-like splitting amplitude is already quite complicated. So Catani predicted all these kind of epsilon pole terms. But here, okay, in our recent work by Feynman integral computation, we calculated this kind of red underline, this finite piece of the splitting amplitude, so which complicated Catani's formula. So I just quickly say something off topic. So we consider this kind of scattering amplitude in the collinear limit, but collinear actually means two ways. So usually people talk about collinear, that means time-like collinear. So time-like, let's consider like two particles, they are both outgoing. So in this case, so it's well known, okay, well established that we have a strict factorization from tree level, from one loop level, from two loop level. So that's all for the amplitude. So this kind of amplitude, okay, so we can just say the PAPB collinear. The P is a PAPB combined to one particle, so it's one point field amplitude. So this kernel here is this board font as SP is called a splitting amplitude or called a splitting function. Okay, it's a kernel. So this contains the divergent piece, okay, of this collinear kinematics. So here the strict means this formula is simple. So why is it simple? Because this kernel only contains three particles information. There's two collinear particle and one combined particle. All the quantum numbers are somehow compressed here. Okay, so this is a well-established work. I think David did a lot of explicit computation on this kind of function in NX4 and also in QCD. But for space-like, so this one is less, okay, less simple. So the thing is, let's consider one particle which is incoming. One particle is outgoing. So suppose that the two partons are almost, so one incoming parton and one outgoing parton almost the same direction. So this is called a space-like, okay. So all you can say, okay, in this kind of west coast matrix signature, this PA.PB is negative instead of positive. So Catani shows that this factorization, you have some generalized factorization. Generalized that you still have some formula one loop like this, but this kernel looks more complicated. So if you calculate this kind of one loop kernel, you find that it contains this kind of complicated term. This T, this is this kind of a color operator. So the thing here is you have this kind of kernel, it seems that it's factorized, but this factor, okay, here, okay, depends on the color of other kind of non-collinear particles. So it's an entanglement. It's not strictly factorized. So this formula is quite complicated. And the thing here is the formula is quite non-trivial. You can think that it's analytical continuation of the time lag, but actually it's more complicated in my language because the thing here is you would have some kind of dependence of all these kind of Mendelssohn variables. So sometimes you have to pick up this branch cut up or down, up or down. So it's quite complicated analytical continuation, I would say. And for two loop level, then the thing is the formula is quite long, it's complicated. But as I just shown here, we finished this computation and we get this finite part, this complicated part. Okay, so for the first line, this is called dipole contribution, and for the second two lines, we call the tripole contribution. So I show that, so how did we get this result? So we did that in the NX4 super Yamil theory because the amplitude is simple, but we did that for both planar and non-planar. So we cannot just use BDN's answers to guess the form of this kind of amplitude. So it's a non-planar part is quite complicated. So the thing is, it seems that it should be a quite simple thing, okay, to try to complete Catani's formula. But the thing here is we definitely claim that, okay, before the pandemics, we solved the two-loop 5-point massless mass integrals, okay, but it has some kind of limitation. The main limitation is we solved that for weight 0, weight 1, weight 2, they are all in this kind of classical polylog functions. For weight 3, weight 4, we know that if we really rationalize all these kind of square roots, the result should be written in terms of GPL function, but we didn't do that. Okay, because we think the GPL function is too long. And afterwards, okay, so you can see this, so there's a package, okay, there's a package called the Pentagon MI that contains two loop 5-point massless and one mass, all the integrals. They also did that in this way for lower weight functions. They just list the simple one. explicit expression, but for weight 3, weight 4, okay, so instead of using GPL, they write it as a one-fold integration. So that one is very, very fast for Monte Carlo. It's very, very good for phenomenology, but it's not so something so useful for our purpose. Because here we want to answer yes or no. Okay, so it's an analytical question. So another thing is we can definitely continue some work before the pandemic. Say we rationalize the square root and then we calculate the weight 3, weight 4 GPL functions. But then this kind of analytic expression is too long, and what we need is just the very special case. This space-like linear region. Okay, so in this case, if you have a very big GPL function, and then you take this space-like linear region do this kind of limit is also quite difficult. Okay, so here we do it until in this way. We just go back to the canonical differential equation. We have the canonical differential equation for 2 loop 5-point massless mass integrals. And then we solve it again, but we solve it in an approximate way. So we just solve it for this pink region. Well, this is space-like linear region. So we start from something we already know here. The x0 is a generic point for the physical region. Okay, for the 1, 2 to 3, 4, 5 scattering region. So this one you can get the analytical boundary value from their package Pentagon MI. And then we solve the differential equation. So first to a special point in this pink region. Okay, so this can be done by this special, very special curve. So on this curve, the square root is rationalized. So everything is solved as GPL function. So at that point, so here we can use some PSLQ algorithm and then try to go from this kind of numerical values of GPL functions back to some very simple numbers. And then x1 is analytic. And then we solve it again by two paths from x1 to p prime to p. Then we get the mass integral analytically in any kind of generic point of this pink region. That's something we did. So in total, we have a huge number of mass integrals, almost 30,000. But then we did that all for this region, all in GPL function. So including both planar and non-planar integrals. So everything analytic. Then we use Carrasco and Johansson's paper 12 years ago, this 2 loop 5-point integrand for planar, non-planar. So we plug in all this kind of integrals, we see a lot of cancellation. So immediately we see the cancellation. All the GPL functions are actually just simplified HPL functions, just by some algebraic recombination. And then we use polynomial tools. We find that for this nx4 amplitude, everything actually simplified to Li classical polylog functions. Then we have a very simple analytic expression for this amplitude for that region. That compare with the 2 loop 4-point planar, non-planar nx4 amplitude. We get the all this kind of missing terms, all this kind of missing terms. So especially we find some kind of very complicated variable, this kind of zi variable, but this kind of variables would be some kind of cross ratio of the spinor, this kind of spinor products, but I'm not going to talk about the details. So I just say that this analytic expression is very, very important, just by solving this kind of differential equation in one particular region. Okay. Analytically can find this complicated dependence. So if you are interested in this kind of complicated variables, we can talk, we can have a discussion after my talk. And also, we are working with Edinburgh group, with Ilan Gadi's group, try to determine how do we get this very complicated dependence from the regional analysis of Feynman integrals. Okay. Okay, so this is my side plot. So main idea is I try to persuade you that this analytic computation of Feynman integrals is important and useful. And then there's a main plot, 2 loop 6-point Feynman integrals. Okay, so we do this because yes, so the space-like means the thing is one incoming and one outgoing particles. Yes, yes, yes. Yes, yes. Okay, thanks. And also thank Inan for the answer. Yeah. Okay, so this is the main plot, this two-loop 6-point. So we will explain this as a kind of a canonical differential equation computation for the frontier of the scales. Okay, so here I just list some examples of the typical two-loop computation from canonical differential equation. So a while ago, we had a lot of 5-scale computations like two-loop 5-point massless integrals. And then, okay, for this phenomenology purpose, then there are many papers about the 6th-scale two-loop 5-point. That's 5-point plus 1 mass, like this. And recently, there's a 7th-scale. Okay, 7th-scale canonical differential equation computation for Feynman integrals. The purpose is to do TT bar H amplitude, but this is one particular sub-process of that. And our work, this two-loop 6-point thing, we will say that it's a scale frontier, right? So that's 8 scale, 8 variables. So namely, you can call this kind of variables as independent variables. Well, but actually how many variables are there really depends on the scheme. So we can say that justify a little bit to say that we do this kind of computation is try to do some next leading order 4-jet production or this 2 jets plus 2 photon production. Okay, but still that's quite far away. This is only the Feynman integral level. Okay, so what we achieved in the recent paper, so what we did is for this kind of truly 6-point Feynman integrals in dimensional regularization. Okay, so we did the canonical computation. So we get this kind of diagrams, a double box 6-point, this pentagon triangle, and also this hexagon bubble. And also we had something unpublished. So for this higher level, for this pentagon box. Okay, so this one is also solved by the canonical differential equation method. But this one, okay, the problem is this one cannot be calculated by EM flow. So we have nothing to compare with. So that's the reason we didn't publish that. We need some numerical check of our computation. So the problem with the EM flow like method for this kind of diagram is the IBP simply doesn't work. The IBP will stop. Even numerical IBP doesn't work. Yes, no matter you use Kira or you use file as the input of EM flow, that doesn't work. It will get you some kind of error message, and we already send the error message to EM flow group, and they sync the error message. The errors is coming from Kira. Yes. Yes, but we also predict that even Kira can do that. It takes a very long time. Yes, it's very long time. But right now, get error message for this kind of thing. So here is almost, we'll say, the boundary of the EM flow computation. But this is not the end of the story. Okay, I had some diagram which I didn't list, which is a pentagon. So this one we can also set up the canonical differential equation, but we didn't. We just get the cut solution yet. We didn't get the full solution. But that one, if you try to do EM flow, it will be more complicated. Okay, so this is what we achieved. So I have to say one thing. So there are very spectacular progress by the bootstrap method for NX4 super Yang-Mills 6-point amplitude. Okay, so I list many classical papers. So people already did it for very high loop. So why are we still calculating this kind of a 2-loop? Okay, people already did 6-loop, 7-loop. Okay. Because that's a kind of different kind of computation. So this one you have the dual conformal symmetry. And also this is the development for the planar amplitude. Okay, so with this kind of symmetry, then the number of letters is quite small, 9 letters, and then you can use the bootstrap to get the amplitude. But here, okay, we are doing this kind of computation, okay, for the Feynman integrals. Okay, these are integrals, not a theory. Okay, I say most integrals do not have this kind of symmetry. Okay, that is one thing. And also we did that in dimensional regularization. Okay, then to get this kind of epsilon expansion is also something quite complicated for us. Okay, so it's a different story. And also for planar InX4, you heard of this theorem from Nima. So a lot of like this kind of bubble or triangle sub, this kind of this Feynman integrals with this kind Feynman diagrams with this kind of subtopology should not appear. But for us, we are calculating the Feynman integral family, so everything could appear. So I would say it's a different kind of computation. So we say we are still doing the two loop. Okay. Okay, so first I want to copy something from actually from Pietro's talk. So for two level 5 point, so everything I would say is still quite standard. But here I still have some question. I don't understand that well. That is the scheme dependence. Okay, so I said that for this kind of computation, I have 8 scales. Okay, but actually, if you change to a different scheme, I think from Pietro's talk, it's called a CDR scheme. So in this CDR scheme, if you consider all the external particles in the d dimension, d bigger than 4, then actually have 9 Mendelssohn variables. But if you consider all the external particles in the 4D, then you have this kind of gram-determined constraint. Then you have a nonlinear constraint. You have 8 variables. So far, we did both, but the published result only contains this one because we think this one, well, you have one field scale. Seems that it's simpler. Okay, so I will say something about this scheme we didn't publish. Okay, so if you do this kind of scheme, so the first thing immediately say you find that very strange. The number of mass integrals depends on the scheme. So for example, okay, we didn't see in our paper, but for this one, if you do this kind of 4D scheme, then for this sector, there are 7 mass integrals. But if you do 9 variable, okay, this CDR scheme, then you have, so if you do the 4D, you have 7 mass integrals. If you do the CDR, you have 9 mass integrals. You have more mass integrals to solve, more complicated. But also there's something, yeah, sure. Yes, depends on scheme. And there's something which is more interesting is actually, if you can see our discussion in the paper, that is also the functional type depends on the scheme. That's a little bit surprising. So for the pentagon two loop 6 point diagram, if you do the dimensional regularization, you can find that, okay, you definitely have a different number of mass integrals. But on one scheme, on this simpler scheme, actually, it seems that we can get the canonical differential equation without problem. But for the other one, we couldn't. For the other kind of scheme, for the pentagon 6 point diagram, then it seems that if we do this kind of maximum count Baikov analysis, we are going to get elliptic function. So that's something a little bit puzzling. So the functional type depends on the scheme. So that's something we discuss a little bit, but we don't have a very deep understanding of it. Okay, so you think that is for some higher expansion of the epsilon, there could be some more complicated functions. Yes, yeah, could be, yeah. Okay, so for the rest of the talk, I just review what is the status of this modern canonical differential equation method. I would say that still to determine the so-called UT basis, the good integral basis is complicated. So here, that's example for this diagram, two loop 6 point, okay, in this 4D scheme. So there are 7 mass integrals. So that's a list of this kind of UT integrals. To find that takes quite a long time. So basically, we borrowed a lot of ideas from X4 theory. So basically, we borrowed a lot of chiral numerator ideas from this paper. So the thing is, this kind of chiral numerator will give you some very good 4D integral with constant leading singularity. And in many cases, they are just a UT integral if you upgrade from 4D to this form minus 2 epsilon d here. But in some cases, especially for 5 point to 6 point, okay, the tricky thing is you have to add some kind of numerator, which is vanishing in the 4D. You don't see that from 4D singularity. But this thing, okay, actually is non-zero, okay, after this evaluation. And also this kind of thing will change your differential equation dramatically. Okay, so this upgrading is not totally trivial. So this experience is not theorem. So our experience is if you just use one chiral numerator. So here that's a chiral numerator. So L1 just loop momentum, and this is this kind of mixed, mixed P1 and P2, this kind of Mason's vector. So this NA, NB are two chiral numerators, opposite helicity. So our experience is you take this kind of linear combination, then this one is usually UT. Okay, we didn't find any kind of counterexample. And one trick is you can do this kind of parity even, parity odd combination. And then in this kind of Mendelssohn variables, I just simplify it easier to some very simple, okay, it's a scalar product or some kind of gram determinant. This is very simple. But something very difficult is here, okay, this is, you have 7 mass integrals. It's very easy to exhaust this kind of good chiral numerators. And then you consider some nonlinear combination, and then some trouble will happen. So for this one, so this one definitely you can use this left, right, this 2 chiral numerators, but combine them together, then you find that you on the cut you get some good term like this. Okay, because here okay we don't have a very good criteria guessing the simple numerator could be UT, but it's not. You have to by hand add this thing. This thing is this kind of triangle sub diagram to get a UT. We don't know the reason for that. We just find that this quadratic combination is not UT. We had to add some kind of this kind of subtopology by hand. Something which is more complicated is sometimes okay we get one UT integral. We have this thing. This thing actually has some hint from this parity odd combination of this quadratic product of chiral numerator. Okay, but for this one, okay, which is more complicated, we have to by hand add this dot in the middle. So this thing is a chiral numerator times chiral numerator plus minus this opposite helicity combination, but also divided by this kind of dot product. We don't know the reason for that. We just spend a lot of time to find this simple expression. So this one is a key step of finding the UT integral here. So I'm hopeful in the future there's some better understanding of this very weird object. And then we get the canonical differential equation. We couldn't get the canonical differential equation directly in terms of Mendelssohn variables. The reason is we have a lot of new factor like this. Okay, so this kind of thing, this kind of spinor products combination, that becomes kind of square roots in these Mendelssohn variables. So we use the momentum twister variables by Andrew Hodges. So this X really means the momentum twister. So we try to rationalize as many as this kind of spinor products variables as possible. And then we try to derive the differential equation. We couldn't run Phi or Kira, all this kind of standard software with Mendelssohn variable with this kind of momentum twister variable because there are too many variables. It simply will stop. So what we did is we make an ansatz of the canonical differential equation. So we have the A-tutor matrix decomposed by the alphabet. And this alpha key here is a constant matrix. So we try to guess the alphabet. And then we try to guess what is the alpha. So we can do this numerical IBP, but we cannot do symbolic IBP for this kind of topology. Then there's a question, so what is the alphabet? So unfortunately, okay, the alphabet is much, much bigger than the 9-letter story, okay, for the two conformal symmetric case. So we have 100 something, the even letters, okay, that's a relatively simple, okay, that's what we polynomial in the Mendelssohn variables. So of course, there's a conjecture to say, can we get all the even letters all from the Landau singularity? I would guess that the answer will be yes, but computationally right now it's quite difficult. I will show that. The more complicated thing would be the odd letter. So this is the odd letter with this up style, down style, this kind of square root will change the sign. Okay, after changing sign of this log something will change the sign under the sign change of the square root. So square roots really means this kind of set of scales, so 16 of them. And also we have this delta 6, which is from the last integral. We call it the leading singularity of the hexagon integral. And also we have some Klein function from the massive triangle sub-diagrams. We also have a more complicated square root times square root letters. So the thing is you will ask that how in practice I can find odd letters. Possibly you can find the even letters by numerically do this kind of IBP many, many times, try to guess what kind of denominators are there. But odd letters will be some very complicated story. So first we say this kind of thing should be found immediately because this is from the construction of the UT. But what is, then we know the square root, then what is the P here? So our collaborator designed a new package. That is, suppose you know the square root, you don't know P here. So there's another conjecture, okay. So from Mandelbrot's group, they conject that for the odd letter, okay, if you multiply upstairs, downstairs, then P square minus Q should be some constant times the combination of the even letters. Okay, so this is their conjecture. So on the other hand, so suppose you don't know P, but you know Q and you know the even letters, then possibly you can find the P. Okay, so that's the basic idea. But the thing is you don't know the constant, you don't know the power. If you just do a brute force search, okay, that's impossible because there are so many even letters. So they had a beautiful way, okay, to reduce the number of the searches and to get a reasonable P polynomial here. So in this way, quickly, okay, just in several hours by laptop, we find these candidates of odd letters. Okay, so this is a key step. This is quite difficult, but we did that. So we have the complete list of this kind of alphabet is already more than 200, okay, but still for the two-loop 6-point, okay, even for the planar ones, it will be more than that because so far we didn't really go to the top topology. Okay, but it's already quite complicated. So we have more than 200 letters, but to fit the canonical differential equation, okay, then you just need to run this numerical IBP 200 times, then you get the analytic differential equation. So otherwise, that's impossible. So we did that with finite flow. That is also quite fast, several days on our workstation. So I have to comment one thing. So possibly someone knows this better than me. That is for the even letter. Okay, so suppose we don't do this kind of brute force fitting. Okay, fitting from this differential equation. So suppose we try to say from a Landau singularity from, for example, the principal Landau determinant package. Okay, we tried that, but the answer is not complete. So here we have 114 even letters, but definitely this software didn't find all of them, unfortunately. So I think there could be some kind of computational problem here. So we say this is conjecture. We didn't get all the even letters from this one. Okay, so especially I can say something that is for the simpler diagram. The observation is this diagram, actually this package is very good, predicts all the even letters. But for these two, they both missed some of the even letters. Okay. Okay, that's the letters. Then the boundary value. Okay, so nowadays we can use AM flow to find the boundary value. Okay, so I say that if you don't go to the pentagon box or pentagon diagram, the AM flow is still very good. You can get 100 digits for the boundary value. But for our family, okay, since this one is massively is very symmetric, then the thing is we can find the boundary value analytically. So we pick up this very special point in the Euclidean region. Okay, sorry, I list 9 variables, but actually we just use 8 variables. So one of the variables dependent. So we use the way that is we just construct some curve from this starting point and do this analysis of the spurious pole of the differential equation. And then we try to determine the boundary value. And we also borrowed some literature because some sub-topology integrals are already known. So we just copy from the literature. So combine them together, actually we find all the boundary values. So I just list for the top sector. So they are extremely simple on this very symmetrical point. And some of them just by this parity is simply 0. Okay, now that. The rest, the most complicated ones will be just some root of unity and take this Li2 function. So this is the boundary value. So it's analytically solved. And then we solve the differential equation. To solve the differential equation, okay, again, we have the 2 to 5-point problem. Because here, you see, we have a lot of square roots. So we use the momentum twister. So this one is rationalized. This one is also rationalized. But this kind of Kalin function is not rationalized by the momentum twist approach. So we have 5 of them. So we didn't try hard enough, okay, really try to rationalize it all together or maybe on the path one by one, okay, so we are going to have some other people discuss that, how to do that, okay, efficiently, but right now I think it's very, very difficult, okay. So the thing is just like the Pentagon MI package, so we can see that for weight 0, it's just a boundary constants. Weight 1, weight 2, the log function and the classical polylog function. So this kind of thing can be relatively easily solved, okay, in terms of simple functions. But what about weight 2, weight 3, weight 4? Okay, so weight 3 would be a one-fold integration of weight 2 function. Weight 4 would be a two-fold integration of the weight 2 function. But here we use the one IBP identity on the integration path. Okay, so we do this kind of thing here. Then we get a one-fold integration. Okay, that's just like the Pentagon MI package. So if you think this kind of thing is for the for this kind of phenomenology study, that is quite good because the one-fold integration is quite fast here. So we have some kind of proof of the concept program on mathematical to do this numerical evaluation. So if you have like 20 digits for this kind of solution, then you just need several minutes. Okay, it's quite fast. But still, we don't call it completely analytic, just like what I shown there. So 2 to 5 point, although everyone says that it's fully analytic, but actually it's not in the package for this kind of weight 3, weight 4, they are one-fold integration. Okay, so it's almost there. I just want to say something, okay, something about the 3-loop 5-point from integral. Okay, that's actually that's from the request from Professor John Ellis. So once I think I gave a seminar talk about the computation of 2-loop 5-point matrix integrals, but then he's definitely asking about the 3-loop 5-point from integrals. Okay, so this is very complicated, but also it's related, okay? Because if you want to do this kind of N3LO, this 5-point scattering, then definitely, okay, you need this 2-loop 6-point input, okay, for the infrared cancellation. So this one, what we achieved is, we not published that yet, but for this diagram, this planar diagram, okay, if we do it with a canonical differential equation with a dim-rag scheme, it's quite possible. We have 316 master integrals. For this particular family, we still have 31 letters, like a 2-loop 5-point case. So we know the letters, we know the mass integrals. We found the UT basis. Actually, to find the UT basis is much easier than 2-loop 6-point. But then the IBP is horrible, okay? So we tried all this kind of commercial software, Kira, or file, they simply don't work for this kind of thing. Especially for file, if you just enter this kind of diagram, immediately get error message because you have too many ISPs for this case. Okay, it's beyond the index system. For Kira, simply we cannot run it. Okay. So the thing is, we used our package, NIT-IBP. Okay, so this package is a package to do this kind of syzygy computation and to give you much shorter this IBP relations. So we first do this kind of NIT-IBP to find the syzygies. So people would think that the syzygy computation could also sometimes be difficult, but this is cutting edge example. We say even for this kind of very complicated 3-loop diagram in dim-rag, NIT-IBP can find the syzygy vectors, can really give you very short IBP relations. And then we feed this kind of IBP relations to Kira. Then Kira can do that. Okay, so that's something we did with our package. So then we checked that we get the canonical differential equation. So this one is done. So what something is missing is what about the boundary value? Okay, that's complicated. I said that Kira or Phi cannot run this diagram, even numerically. So AM flow couldn't run this diagram. So we couldn't use AM flow to find any point, no matter boundary point or generic point. But if we go down a little bit for this diagram called the rocket diagram, that's simpler than the top topology. Then we can say the Kira can run it. And then we can get this boundary values of 100 digits. We can even do some kind of analytical fitting of the boundary value, but this boundary value is not fixed yet. Okay, so I think I do a summary here. So the main plot I said is we did this analytical computation of the 2-loop 8-scale Feynman integrals in the dim reg scheme. And we are also working on the 3-loop 5-point Feynman integrals. So we already made quite some progress. So we think that the analytic computation of many more multi-loop, multi-leg, multi-scale Feynman integrals could be possible. So something I didn't talk in this seminar is so far to find the UT integrals is very difficult. Okay, although we borrowed a lot of beautiful ideas from chiral numerators from the Engels-4 theory integrand, still that's not enough because our integral is not in 4D. We are still missing a lot of pieces. Okay, sometimes we are really just following the direction of beauty. Okay, we try to find some nice, beautiful integrand, and it's more likely that that is UT. We don't know the reason for that. It could be a quite good problem for AI. We think use AI to find the UT integrals. The boundary value, okay, is still a big problem. Okay, in some cases, we can use AM flow or some way to automatically find well, this high digits boundary value, but in principle, okay, if some integral is a really multi-loop or really multi-leg, then the AM flow couldn't run. We couldn't find the boundary value. And something definitely I didn't talk would be this more complicated functions, elliptic function, hyperelliptic, and Calabi-Yau. So please refer to Sebastian's talk this morning. Okay, so that's all of my talk. Thank you so much.
Questions?
Yeah, thanks for a very nice talk. I guess it's two-part. First, so in this TT-bar Higgs computation, they found for the first time also not just odd letters, but also like nested roots appearing in the letters. So I'm guessing even in neither of these two cases, you found anything similar in complexity?
For the sorry, so what is the statement of the number? You have some statement about the number of roots or something.
Sorry?
You have some statement on the number of the roots.
So this was this Higgs to TT bar Higgs TT bar Feynman integrals by Ben and collaborate. And so there they found nested root. They didn't just find like single square roots or products of square roots, but also like nested square roots.
Yes.
So this didn't appear anywhere in your.
I think it's quite a general. You say for this one definitely have this. Well, you mean nested square root, but we have this is not nested. This is a product.
Right.
No, we didn't. We didn't find the nested square roots.
Okay.
Yes.
And second, and maybe this is somewhat related to, on the next slide, you said there was this relation between the odd letters and the even letters. This is maybe my own naivety. Is there some understanding whether this should generalize somehow to like these nested or to what happens if you have, for example, nested roots?
We don't know.
Okay.
I think that this feature is not in this package yet, but I think it's a very good question. I will ask our collaborator to try that case.
Okay.
Yeah, but I can say something about this more trivial case. Okay, it's not nested, but it's productive. Okay, so for this kind of thing here, we did something very naive. Okay, so for the package, actually we combine these two together, Q1, Q2 as one, still called one square root. Then we just take more computational time to find that because of high power. Okay, but for nested, we need to think of that.
Okay.
Yes. Thank you so much.
Okay, thanks.
Okay.
Any other questions? Okay. I suppose I might be permitted one. I mean, we all love archaeology, especially in a city like Florence, but why is it that people actually want to calculate CDR scheme integrals? What's the motivation for that?
So why should we consider the CDR scheme and this scheme here?
Yeah.
I'm not quite sure because I'm not from the field of this infrared subtraction direction. So what about if people consider N3LO cross section? So do they need to do this kind of
you can and should do everything in the Veltman scheme. So
Well, but in order to do this kind of three loop between this subtraction between three loop or two loop, do you need to create some kind of d-dimensional photon, d-dimensional?
Yeah, but you don't need to do the externals in D dimensions. We're not actually living in D dimensions, and you're basically. I mean, I could almost quote Warren Siegel here, but the Joseph knows the chocolate cake story, which I'm referring to. But so you put in a lot of stuff to only take it out at the end. It doesn't really make any sense. If there are no further questions, then let's thank Yang again.
Okay, thank you.